So our second example is dealing with bicycles. It says bicycles arrive at a bike shop in boxes. The means and standard deviations for the setup phases are given in the table below. So we have an unpacking phase, which on average takes 4.5 minutes, and a standard deviation of 0.7 minutes. The assembly phase, on average 21.8 minutes, with a standard deviation of 2.4 minutes. And then we have the tuning phase, so average of 12.3 minutes, standard deviation of 2.7 minutes. So a customer decides to buy a bike like one of the display models, but wants a different color. The shop has one still in the box, and the manager says they can have it ready in half an hour, so 30 minutes is what he is promising. We're going to find the probability that they can get the bike set up and ready to go as promised. And there are a couple of things that we're told. Based on past experience, the shop manager makes the following assumptions. The times for the three setup phases are independent. So this would tell us that it's okay to find the standard deviation of a combined variable, which is likely what we're going to want to do. And then the second thing we're told is that the times for each phase are approximately normally distributed. So that will help us in a moment in finding a probability. And as you probably guessed, we're probably going to use the normal model. So our first step is we're going to go ahead and find what the mean and standard deviation of the combined time is. So we're saying the total time it takes to do all of these things for this one bike they have in the box. So we're going to find the average, so we're finding average of the unpacking plus assembly plus tuning. So again, our mean for expected value, the rule is we can do whatever we want and basically exactly what we would expect. So 4.5 plus 21.8 plus 12.3, which is 38.6. So on average, it takes 38.6 minutes to put a bike together. So already we're kind of seeing that half an hour promise is not super likely since our average is higher than that. So then we're going to find the standard deviation of the combined time, which again we can do because we were told each phase is independent. And again, just like we talked about on the last example and the last class, when we're talking about three separate random variables, I can't just add their standard deviations, I have to add their variances. So I'm going to add the variances first, so 0.7 squared plus 2.4 squared plus 2.7 squared would give me the combined variance. And then if I want the standard deviation, I would just take the square root of that. Right? And that would give me a standard deviation of 3.68, we'll say, minutes. So on average, it's taking 38.6 minutes, but the standard deviation, the typical difference from the mean, is 3.68 minutes. We can see that our 30-minute promise is more than one standard deviation below the mean. So again, we're kind of already seeing that this was maybe a little bit too much of a promise. But now we're going to actually find that probability. So because they told us that each phase is normally distributed, that would also mean that the combined time, when we add them all together, should also be normally distributed. So what I'm going to do now is I'm going to draw a normal model. So this is taking us back to quite a while ago. Our mean we learned was 38.6 of our combined time, and then we have that standard deviation of 3.68. And so one of the things we could do is actually add and subtract 3.68 3 times to figure out what these kind of standard deviation numbers are. I'm not going to do that right now, but we could. Right? So then we're going to find a z-score like we always have, and our z-score is based on this 30-minute promise because we're trying to find the probability that he can get it ready to go within that 30-minute promise. So I'm going to find a z-score for 30 minutes. So 30 is my observed minus the mean of 38.6 divided by the standard deviation, which is 3.68. And that gives me negative 2.34. So we're talking about 2 1/3-ish standard deviations below the mean. So we're way down here. And so we're finding the probability that you can get it ready to go as promised. Just generally with normal model probabilities, it's never a good idea to find the probability of a single individual number. We always want to find some kind of range. So he said 30 minutes, but it would also be just fine if it took less than that. So I'm going to find the probability, so P parentheses, that the combined time U plus A plus T is less than 30, or less than or equal to. On a normal model, less than versus less than or equal to is not really something we're worried about. So then at this point, I would use my Z table, or you can use your calculator. We can do, oops, go back to that. We can do the second var's normal CDF. Remember, our lower bound would be -1 E99, since we want to go all the way to the left forever and ever. And then my upper bound would be my Z-score, -2.34. Don't actually know if we talked about it in this way. That is another way you can use the Z table, or the calculator. You can also use just your Z table, would be fine as well. Right. So we get a probability of 0.0096. So there is a 0.0096 chance, so a 0.96% chance that it would be ready to go as promised, which is not looking super good for this manager. It looks like he overpromised.